So hello, welcome back to this discussion of turbulence modeling. I'm still discussing the cases, this one. Last video we're talking about FV schemes and some of the FV solutions and boundary conditions. But this video I want to continue that discussion with FV solutions. So first we talked about what GAMG is. It's basically taking the fine mesh. We solve the fine mesh solution by starting out with a coarse mesh solution and mapping it onto the fine mesh as an initial condition. Okay, so initial condition or initial guess. So I mean the concept is pretty nice, but it may not always scale well. I mean there is some nuance, so you got to think about how to, you got to kind of experiment around. But in general, for pressure, GAMG is pretty okay. It's a multi-grid method. That's why we have this multi-grids. Okay, PCG. What is a PCG and what are these preconditioners? So some of the good links that help in this document, but I can also post it in the description. So and there's a lot of things to do here. For example, you have this in this simple form, you have PRGH, you have residual control. I kind of talked about my residual control before in my OpenFOAM video, so I'm not going to talk about it here. This will be found in, let's say, the OpenFOAM intermediate playlist. And again, the description video is the link for the playlist is in the description. Okay, there's a lot of things, so let's take a look one thing at a time. Okay, so for example, let's take a look at hot room, because this is a pimple foam case. We can go to system and fvSolution. Okay, so when you see for pimple foam case, you will see, okay, there's a row something here which you need to solve. There's a PRGH, and then you have all of these. And what this row dot means, it means that it's row and what, and it could be a row final as well, because this dot star is a wildcard. Means any line of text that comes after row, it is included. So PRGH, for example, if you want to do the same, not exactly want to do the same, but you usually need to define two things. One is PRGH, one is PRGH final, and it may be very confusing what these things are at first, but you need to define both of them. So everything, for example, U, H, E, K, epsilon, and R, they will need to have a final entry here as well. U, H, E, K, epsilon, R final. So if you want a row and row final, okay, I'll just talk about that first. Row and row final, you can use this wildcard. Row dot star final. I mean row dot star, not final. You have a row dot star, that means it will represent to say I'm using these solver settings for row and row RGH, or anything that comes after, because this final, typing this thing out is a little bit troublesome. So I guess this guy, this person here, wrote it like that. So anyway, what is this? What is this, the difference between row and row final, or PRGH and PRGH final? Why do you want to have different settings? So if you remember the piezo algorithm or pimple algorithm, they use one momentum predictor step. Okay, one momentum predictor step. I'm not going to go through all this here. One momentum predictor step and a number of corrector steps. So you can see you have a momentum predictor, and this is the so-called outer corrector step. N correctors, these are the pressure correction term. So these are faster. So N correctors, we have multiple iterations, and usually the first iterations they deviate a lot from the true value. But the last iteration, this actually doesn't what do you call that? Does not deviate too far from the actual value. So you can either choose to be more stringent so as to get it to iterate more, or you can be kind of lenient. You can actually make the tolerances less or more depending on how fast you want to converge and how accurate you want. For example, you have this PRGH here, where you have this tolerance of 1 times 10 to the minus 8, relative tolerance of 0.01. For PRGH final, you will see this $ PRGH here, meaning to say I'm going to copy and paste all of these settings and put them here. However, when you define all of this, it types here relative tolerance, rel tol is 0, meaning to say all these three remain the same. I just change this relative tolerance from 0.01 to 0, so that the iteration only ends after the final, only after the tolerance, I mean the error is actually 1 times 10 to the power minus 8. That's the absolute value. So this is an example of how to make one of these things more stringent, because if what you're saying here is that if the tolerance is less than 1 times 10 to the power 8, or the relative tolerance is less than 0.01, which means this relative tolerance, of course, you normalize it with the last value you had, the residue, so-called residual whatever. So not exactly residual, but anyway, yeah, I think it is. Anyway, yeah, but anyway, when you iterate, basically you are saying, okay, I don't want this relative tolerance to guide how accurate my things are. Okay, this tolerance here is a lot stricter. So this is I mean, after I finish iterating, I want this tolerance level of 1 times 10 to the power of minus 8 to be met. So relative tolerance is 0. So this kind of makes this stop condition, because your simulation or this iteration can stop either when the tolerance is 1 times 10 to the power of minus 8, or relative tolerance drops below 0.01. But I don't want this condition to hold anymore. I want this to stop. So so it defines it as 0, so that the simulation will only the iteration will only finish, or the corrector step will only finish when this tolerance here is met. So this is one example of making the so-called last iteration a lot stricter. So overall, the idea is that when you have this PRGH and PRGH final, you want the last one to be more stringent and the first few ones to be kind of more lenient, so that the iterations can sort of go faster in that sense. Okay, so this is what the P and P final are. GAMG and PCG. What is PCG? PCG is they call it preconditioned. Okay, that's what the P stands for. Precondition conjugate gradient. So that's a complicated term, numerical method. I'm not going to go through too much detail here, but it's basically we normally talk about Gauss-Seidel for solving systems of matrices, but this conjugate gradient method is sort of more advanced and more stable than the Gauss-Seidel method. So we can read some of the reports here. And just to try and remove some confusion, we want to see what preconditioners are, and sometimes you will see this smoothers, and it can be a lot of confusing terms. So I'll try and briefly clear up some confusion. I won't say what these methods are. I'll just give you a rough idea. So a preconditioner is this. Basically, if you try to solve a system of matrices like what we are describing before, we have this simultaneous equation system, AX equals B, linear system of equations or matrix. Okay, sometimes to solve this, you want to take A inverse on both sides so that you can solve, but finding the inverse of A may be a little bit difficult. I mean, solving the inverse of A may be very computationally intensive, plus you're going to do it multiple times over every time step. So you got to find a way of of ensuring that your iteration, the solving method of the matrix, is very stable and is also fast. So one of the ways is to multiply A by some preconditioner. So it can be, for example, the inverse, a random matrix, we call it M, or maybe some inverse of M, or whatever. The basic idea is that you multiply A with some kind of matrix, so that it makes the situation easier to solve, computationally speaking. So less iterations are needed. That's all preconditioners are supposed to do. Now smoothers are similar in function to preconditioners. So they try and reduce the number of iterations, but as the mesh grows, the number of iterations also grows. Preconditioners, they reduce the number, their purpose is to reduce number of iterations, but as your mesh grows bigger, the number of iterations required also grows bigger, right? So let's say you have a small mesh and you require this number of iterations if you don't have a preconditioner. Okay, small mesh. So with a preconditioner, maybe you need less iterations. So you have number of iterations here. Okay, you have a number of iterations here. Alright, so with a small mesh, when you have a bigger mesh, maybe your number of iterations grows. Number of iterations grow, but the thing is that, okay, maybe a preconditioner will still reduce a number of iterations, right? But when you can see, when you have a very big mesh, this small difference here will start not to make as much of a difference. A small difference, right? As compared to here if you use your preconditioner, maybe your savings on time, computation time, a lot more. So what you can do instead is very similar. You change the matrix A. You change this matrix A by using a smoother. Maybe you don't multiply it by some other matrix, but you can maybe do some decomposition or whatnot. But the idea is to basically change the matrix up a little bit or do some mathematical manipulation to make this easier to solve. So in that sense, preconditioners and smoother, the intent of them are pretty similar. It's just that you have lots of options, okay? So as you can imagine, matrices are not very symmetric. And what's symmetric and what is not, how they come about. So you have your PDE. You have your PDE here, okay, which you try and through your FV schemes, you turn into a system of matrices, AX equals to B, right? Okay, so what is this A? This A, sometimes you will have a diagonally dominant matrix where most of your terms are here, and this is pretty symmetric, right? Symmetric in the sense that, okay, if I draw a line here, the terms here look very much like the terms over here. Okay, that's a symmetric matrix. But in general, you cannot expect matrices to always look so nice. So that's called an asymmetric matrix. So asymmetric matrices, as you can imagine, are a little bit harder to solve. So what are some kind of preconditioner or smoother you can use? You can use this DILU. It's a diagonal based incomplete LU decomposition. So I hope you know what LU decomposition is, the lower upper matrix decomposition. So some of usually which matrices are asymmetric. You have your velocity equations, which is your momentum equation mostly because you have a momentum partial differential equation 3 directions. So you have all these things going on, a bit complicated, and you have many terms, like you have a viscosity term, you have convection term, so you have time dependent plus viscosity term, convection term, equals, you have your viscosity term plus a turbulence plus source, etc. So usually this convection term actually makes gives you a lot of terms for this matrix, for this matrix over here. So it will kind of mess up the symmetry of it, because you have so many interdependent terms over here. So it makes the matrix very asymmetric. For that, DILU, diagonal based incomplete LU decomposition, is pretty good for symmetric matrices. But let's say for equations such as pressure equations are more symmetrical. You do not see the convection term going hand in hand with the pressure equations or Poisson equations or whatever. So usually you can use this DIC class. Okay, so this one there are many kinds. I won't say what DIC is, but you just take it as a rule of thumb. There's a lot of detail here. Anyway, if you want more background on this, you can take a look at some of these things. And a very good thing to learn is called the Krylov subspace methods. These are the foundation of how you get your conjugate solver. This CG, PCG, PBICG, as you can see here, PBICG. This is a precondition by conjugate gradient solver. And then of course this PICG step is with some stability, some modification to make it more stable numerically speaking. So you can see your pressure equation uses PCG, which is actually pretty good solver for what do you call it, symmetric matrix. And your preconditioner, as you see here, you can use a DIC. And of course for all these asymmetric, you see that the preconditioner here used is DILU. So this is how you can kind of see which is good for which. You can actually take a look at the OpenFOAM fvSolution files, see some recommendations there. Okay, or see what other tutorial files use, and you can copy accordingly. I mean, now that you know all of a little bit more, which preconditioners or smoothers are useful for asymmetric or symmetric matrices. So let me do this, just that I don't confuse. So these are actually also preconditioners rather than just smoothers. Okay, these are preconditioner. Alright, so where do you see smoothers? We do not see smoothers when you use this precondition kind of solver here, because this P actually stands for preconditioner. Okay, alright, this P actually stands for precondition. So over here in preconditioners, you will see this precondition solvers, you will see preconditioner entry here. Otherwise, you will see smoothers, okay, which is, for example, in this box turbulence, where you'll see this PCG. This is a preconditioner, but you see when you see the U equation, you have this thing called smooth solver, and smooth solver here actually tells you, hey, I'm using a smoother instead of a preconditioner to change my matrix beforehand and solve it. And the smoother here is called symmetric Gauss-Seidel. Okay, similar idea. Okay, so conjugate solvers is a little bit of a complex topic, so I won't explain too much. GAMG I kind of went into before. If you really want to know what conjugate solvers are, you can take a look into Krylov subspace methods and all. Those are very important to know if you want to know about these. I'm not going to go through them here. So we went through the DNS box things, and you can see now for P pressure matrices, they are pretty symmetrical, so that's why we use this PCG solver, conjugate solver with preconditioner. For U, we expect asymmetric matrix, so we use something else. it can be a DILU preconditioner, or even something that's pretty robust is this smooth solver with a Gauss-Seidel smoother. This will help the solutions converge better, especially for very big meshes. So this is good. And if you want to take a look at another example, we can take a look at fvFOAM. fvFOAM is well, there's a challenging. They use LES simulation, so they don't like dispersive equations, meaning to say we use as accurate as possible. Oh, not dispersive, dissipative. Sorry, dissipative. Okay, hopefully you know what these terms are. Dissipative means there's basically it's like a round-off error. All right, a round-off error. So depending on how you discretize your PDEs, partial differential equation, you can discretize using like a fourth order, third order, meaning to say use more polynomials. If you use certain discretization schemes like upwind, maybe you use like only the first term. So there's a lot more error in that sense. So usually we call that error dissipation error. Okay, anyhow, that's the very, very condensed version of it. Okay, so for fvFOAM, we see that this is our LES equation. We use a GAMG method here with a Gauss-Seidel smoother, okay, for PRGH. And you look at the U, H, and K. Yi is actually like the mole fraction or some chemical, could be methane or something. So the solvers used here are smooth solver and Gauss-Seidel smoother. So actually, smooth solvers, the Gauss-Seidel smoother, it seems like a pretty robust thing to use for velocity and everything else. Okay, by conjugate solvers with this DILU is also pretty good. Yeah, this just gives you an idea of what to use where. Just a very rough idea. Okay, so this is the FV scheme setup. We already went through it before. And okay, so I'll stop for now. I'll continue more discussion in the next video. Thanks for watching.